Good morning, I'm Ralph Delmans from Knowledgebase. This is the Operations and Infrastructure session. We have two 30-minute talks. The first one is from Manu Patel from Facebook, and he's going to talk about the DNS infrastructure at Facebook.
Thanks, Ralph. Hi, good morning, everybody. So to kick off DNS OARC 28, let's talk about how we run DNS at Facebook. We have roughly two sides of it. The external DNS has people using Facebook CE, and also the internal infrastructure. So I'm Manu Patel. I'm a production engineer. I've been at Facebook shy of 5 years and a half, and I work in the traffic team. The traffic team is basically responsible of a few things. We are responsible of our layer 4 load balancers, as well as our layer 7 load balancers, our CDN, and our DNS global load balancing, which I'm going to talk about. Facebook has a mission, which is to give the people power to build communities and to bring the world closer together. The way the traffic team can help there is to make sure that the infrastructure is fast to access and also reliable. So if we take back in the days when Facebook only had data centers in the US, if you were a user in Seoul, South Korea, you will be, the closest place you could get to was the west coast of the US in Oregon. By the time you establish the TCP connection and then establish your SSL session, there will be 3 round-trip time. And with 150 milliseconds per round-trip times, that brings you to 450 milliseconds. At this stage, you haven't even sent any request yet that is meaningful to your content. Eventually, you get your last round-trip time, and you get the content over 600 milliseconds. So what did we do? We built an edge network with point of presences, and now we cover a bit more. We get closer to the end user. So if we get back to our user in South Korea, and they cannot connect to a point of presence in Tokyo, this is what it looks like now. We have a 30 millisecond round-trip time. So altogether, these 3 round-trip times will make 90 milliseconds instead of the 450 milliseconds before to establish the SSL connection. Then, to get their feed, they still need to get to the origin. But this time, we can benefit from pre-established connections between Tokyo point of presence and our data center. Altogether, after 240 milliseconds, the user gets the content versus the 600 milliseconds earlier on. Cool, so if we can get closer to the end user, we improve the latency, but now we need to be able to send them to a close-by location. So that's where our DNS global load balancing comes into game. We built a system that we call Cartographer that basically takes inputs and is going to generate a DNS map at the end of it. The type of inputs that it takes are the latencies, like we need to know how long it takes for a user somewhere to get to our different point of presences. We also need to know the capacity. If the point of presence is saturated, we should not send any more people there, or the experience will be terrible. We also need to know the health of the data center, of the point of presence. Things happen, things stop working sometimes, and we may just have a maintenance in that point of presence, and we should not send people there if it's not healthy. Finally, once we found a set of places to send a user, we need to know about the routing. We have peering connections with ISPs and ASs and stuff, and this allows us to have more granularity as to where to send the end user. So Cartographer basically creates a map of resolvers and RTTs to different point of presence. Generates a DNS map at the end of it, and then it will need to deploy it. So roughly, this is what we get. Let's say resolver A, we may learn that there are people beyond resolver A, maybe 30 milliseconds away from Amsterdam, 55 milliseconds away from Frankfurt, and so on and so forth. Resolver B, on the other end, maybe 35 milliseconds away from Frankfurt, while they are 45 milliseconds away from LHR. The natural choice would be to send people beyond resolver A in Amsterdam and people behind resolver B in Frankfurt. But then maybe we don't have capacity anymore in Frankfurt. So in this case, we're going to start sending those people to LHR instead of Frankfurt. On top of that, we can apply rules. For instance, we may need to do some overrides. We may need to be able to override the decision that Cartographer will do. Some ISP may have some specific demand that they will prefer one point of presence over another one, and we need to be able to apply these overrides. So cool. It's really nice to be able to get these list of preferred point of presences, but how do we get this RTT in the first place? This is where Sonar comes into game. So every so often, we're going to send users to get their profile picture from a randomish point of presence. To do that, we generate a unique host name, and we're going to send that to the user to get their profile picture. Because it's a unique host name, it's not in any DNS cache. So we're going to see that in our DNS logs. So there we're going to get the unique host name and the resolver IP. Eventually, the user gets the profile picture, and then we will have another line in logs in our layer 7 load balancers, in our reverse proxies, where we will have the unique host name, as well as the client IP, the edge location where they got the profile picture, and the RTT. If you join these two data sets together, you now have a resolver IP going to an edge location, and you also know the client IP. And then you have an RTT which is associated to it. With enough of these samples, you can start building a map of the connectivity of the people to Facebook, like depending on their networks. So this is what Cartographer looks like in action. The clear green line here is the capacity limit of the point of presence. And the red line is the user demand that will be sent to that point of presence if we were sending them to the best location. During the day, the traffic ramps up and eventually goes to the capacity limit of the point of presence. Cartographer will kick in and will start steering away traffic to make sure that we stay at the capacity limit. During the day, the user demand will actually increase, but we send the traffic away. As the evening comes by, people start using less Facebook, and then eventually the demand will be below the capacity limit. Then Cartographer will stop sending people away. Okay, I mentioned that Cartographer was generating DNS maps, but now we need to deploy that to our DNS servers. So we are a heavy user of BitTorrent internally to deploy binaries and stuff. So Cartographer generates that map and pass it on to a job which is responsible of publishing that. We have a pub/sub system where the publisher will basically compile, so we use TinyDNS, and TinyDNS has a simple assumption is they need to be a data.cdb file in its working directory, and it will pick it up and start serving records from it. So the publisher takes the textual map that was generated by Cartographer. It will create the TinyDNS CDB file. It will run a bunch of tests against it. And if it's deemed to be valid, it will start BitTorrenting it. So it creates a BitTorrent file, starts seeding it, and writes the BitTorrent file onto a Zookeeper node. The BitTorrent file being only like metadata about the actual torrent. On our DNS servers, we run what we call a subscriber. The subscriber will actually pick up that there is a new torrent file and will start downloading it. Pretty quickly, all our DNS servers will be part of that BitTorrent swarm, and a lot of the traffic that distributes that map is actually going to be internal to either the rack or the cluster. Like very little traffic will actually go across clusters. The subscriber will put that map onto the file system where TinyDNS expects it to be, and TinyDNS will pick it up. Finally, now we should have a DNS server which is able to serve requests, but until you actually start saying that you can serve requests, that you have the IP of that DNS server, nothing will happen. So here we have the injector job that has another role, which is to health check the TinyDNS server. It's going to run some tests, and if it's deemed healthy, it's going to inject the IP address into the network, and then we will start receiving traffic. If it's not healthy for whatever reason, the injector will not inject the address, and nothing will be sent to that unhealthy server. So that's the external part of our DNS infrastructure. But internally, we also need to run DNS. We have a lot of servers, and they need to do DNS resolution. So it's slightly different there. Servers have a need for recursive resolvers, and here we use Unbound. We have two kinds of Unbound already. We have one that only serves our internal records, like Facebook on zones, and we have one for a few of the servers that may need to be able to do actually full internal resolution. So in the case of the Unbound local, basically what we do is we configure stub zone to our locally running TinyDNS servers. Here we have two types. We have the external one, which is roughly the one I talked about, but we also have internal records that don't matter to the rest of the world, but that we need internally, be it just like all our server host names and stuff like that. So we configure the stub zones, and the unbound process will be able to actually query the local TinyDNS servers. Having a DNS server running is one thing. Having a DNS server being operational is another thing. So here we have a wrapper on top of that, which is basically a process that manages unbound. Here again, this process will health check unbound, and if it passes the test, then it's going to advertise the IP. If it doesn't pass the test, then it's going to withdraw the IP. But then there is also sometimes configuration changes. And unbound wrapper is responsible of finding those changes, generating a new unbound configuration, checking it with unbound checkconf, and then if it's valid, put it on disk where unbound will expect it. Having a new configuration is one thing, but then you need to restart your servers. So unbound wrapper is also responsible of rolling restart those servers. To do that, we basically take a log on Zookeeper, and so we make sure that only one server goes through the restart at a time. I talked about injecting IPs, advertising IPs. So here we basically use BGP and ECMP. The server will tell the top of rack over BGP that it can serve this IP. ECMP will basically deal with balancing that traffic. And to talk BGP, we use ExaBGP, which is basically a Python software that knows the BGP protocol, but won't do anything else unless you tell it to. So we have a contract with our application where they write a file with the routes that need to be advertised and until when. And then our ExaBGP helper process will take care of advertising or withdrawing those IPs. Externally, we have mostly Cartographer making change to the DNS. But internally, we have engineers that want to make changes. And you have a few people that know about DNS, but then there's a lot of people that want to make DNS changes. So you want to facilitate that as much as possible. And we also have servers. Maybe these ones are the best. They do work 24/7, and usually they don't make mistake. If they do, it's because you program them to do so. So human changes go through code review. One good thing about it is we got version control, so we can get back in time and see what changes were made and for what reason. But also, having code review, then we can make sure somebody catches any issues. But you don't really want to wait on the human to actually come here and say, oh, you put a comma here and it should have been a dot. And they actually may miss it. So we can also run linters and continuous integration where we're going to catch some of the common errors and give actionable items. Things we can detect are like CNAME cycles, somebody putting a name which is not in any of our zones, maybe a typo, or an IP address which is not one of the Facebook IP ranges, or TinyDNS formats or whatever. Once it's landed, it goes into our configuration system that we call configurator, and then it gets deployed, propagated to all the hosts that actually subscribe to that configuration. On the server side, we provide a framework where people that want to generate DNS entries only care about generating the DNS data. And then we abstract away all the details of the storage and like retrying when storage fail or whatever. One thing it does too is we don't write the data directly, we put another level of check here. So that's what the DNS mutator here does. Basically receive the data that the task wants to write. It's going to run checks against it, and then if it seems to be okay, it's going to write it to Zookeeper. If the checks don't pass, then it's going to fail, but at least only that task get impacted. So if you have tasks doing different things, you basically don't want one misbehaving task to break the whole pipeline. And also, in the meantime, while the task is not succeeding to write their data, they still at least have the stale data from the previous runs. Now we get into a situation where we have humans doing some changes on one side, and we also have servers writing to different Zookeeper nodes. So here comes the presenter. The presenter takes all these different configurations together and roughly concatenates everything. It does a bit more than that. It will be able to do validations. This guy actually has the whole view of the DNS map. So then it will be able to run checks like making sure only one CNAME got declared for a given record, not two of them, or like no other records. for the same host name. It will do collision and resolution. Let's say one of the automatic process generates an A record for a given domain, and a human generates another one. Most likely the human wants to override the behavior. So we have a system where we're going to have priorities and be able to resolve conflict that way. At this level, you can also have like tons of metrics that let you know that there is conflicts and what kind of resolution or whatever. We can also do post-processing. Most of the time, if you got A, Quad A, or MX records, you will need to get some SPF records too. And people will typically forget to do that. So what we do here is, at the end of the run, we're going to say, okay, these ones should have an SPF record, and we're going to define a sane one for them. If you declare one up front, then we're just going to use this one. So now the presenter generates the final map, and then we get back to where we were with Cartographer early on. We need to publish that map. So we're going to pass that on to the publisher, and the publisher is going to use BitTorrent. So if you take the whole pipeline altogether, what we've done is we've broken the pipeline into small components, and each of the service does one thing and a simple thing. We try to catch issues at every level. So if something breaks, it's much easier to trace what is the issue, and it doesn't impact the whole pipeline. And also, basically, if you don't impact the whole pipeline, you basically limit the blast of the failure you're going to have. That's about it. Thanks for your time. Any questions?
Paul Hoffman, quick question on your, mostly about outward facing, anything you do inside, of course, is your own, whatever. Tiny DNS?
Yeah.
Has that gotten in your way? Are you super comfortable with it? Have you rewritten it from scratch? I mean, just, I haven't seen that in a, you know, if this had been DNS at some bank, I would go like, okay, I can understand that. And I'm not criticizing, I'm just sort of surprised.
Yeah, sure.
You obviously have beaten on it. What do you think?
So, well, we don't do DNSSEC. And, well, it's simple. I guess what matters, like within the pipeline, it just does one thing, and then we have all the simple components that take care of the rest. We did apply a few changes, like supporting IPv6. We are proud to be pretty much an IPv6 company, and so we've added that. We've enhanced also the way you can do geo-targeting, like what I mentioned about resolvers and being able to assign people behind the resolver to a given POP. We've been able to define basically mapping of given zones to given locations depending on the resolvers. We've also added ECS support and stuff like that. But pretty much, it's simple, and we've been able to iterate on that, and it has been fulfilling our needs so far.
Okay, you just gave the answer, but I found the presentation very interesting, but DNSSEC, I didn't see any signing in the pipeline. So,
yeah, we can have a long discussion, I guess. Yeah, we don't do
DNS. Short
DNS.
and say you're going to do it. So.
Well, I'm not going to say that we're going to do it. I guess tiny DNS for us definitely prevents us from doing it, and I think there may be also other solution.
Hi, Matt Weinberg from VeriSign. I'm just curious how you guys chose to have 2 NS records for Facebook.com. I don't mean it as criticism, I'm just more curious, like, why not 4? Why not more than 2?
I guess at least to be able to, well, we're using Anycast, right? So behind those records, there's a lot of machines serving the traffic. I guess at least we want to isolate subnets. And, well, we got IPv4 and IPv6, so we got 4 maybe.
Okay, thank you, Manu.
Thanks.
The next speaker is Robert Edmonds from Fastly. Robert is going to talk about something that concerns him, which is the disappearing choice of DNS services in home networks.
Hi, my name is Robert Edmonds. I'm doing a talk which is oriented more towards the client side. I think we definitely get a lot of server side and infrastructure oriented talks, but I would certainly like to see a lot more on the client side as well, since if there weren't any clients, there'd be no need to build any authoritative infrastructure. But this is about an issue I've noticed a while back. But I recently recognized it as a trend when I added a second ISP at home and noticed that the second ISP was also doing the same thing that the first one was doing. So most home broadband users, there's millions and millions of them, they generally use a device provided by the ISP. They don't go out and buy something. In general, they get a integrated device which has a bunch of hardware in it, and it's very, very integrated at this point in 2018, and typically have a number of components, at least a modem and a router, Ethernet switch. Generally, they're also Wi-Fi access points because at this point, customers expect to be provided with a wireless access point for their devices as well. So the ISP is responsible for these segments of the home users network, at least informally. And these devices are manufactured by OEMs, and they're responsive to what their customers want, the features that the customers want. But the customer is not the end user. The customer is the ISP buying these devices in volume. So they'll be responsive to what features the ISP wants in the device. So if you're a large ISP and you're buying zillions of these devices, you get to dictate, among other things, the branding and the features that go into the device. So this is a typical home gateway device from AT&T. It's a large plastic black rectangle with lights on it and the logo. This is a typical one from Comcast. It's a large black plastic rectangle with lights and a logo on it. So the device is connected to the homework behind these boxes. They'll typically do two things. They'll use DHCP to get to how to configure the IP address and the other networking information, and they'll have a stub resolver, and they'll also use DHCP to get the DNS servers it should use. There'll be exceptions, but I'm talking about the experience of tens or hundreds of millions of home broadband subscribers. So I'm going to talk about the general case. So these branded gateways have a DHCP server to advertise this information, and they'll have an administrative interface that gives you some control over the parameters that DHCP server uses. But one thing I noticed is that these DHCP servers, the administrative interfaces for configuring them, they lack the ability to set the recursive DNS servers. This is a little bit conspicuous for me and this audience. But in some cases, an OEM will produce the branded device for a large ISP, but they'll also produce an unbranded one with a different logo on it, slightly different set of plastic, and a different firmware image. And I looked at some of these unbranded ones, or at least screenshots from an unbranded model, and they do have the feature to configure the recursive DNS servers. So it's not that the feature wasn't developed and is absent. It's that the feature existed, and at some point, it was removed. I think this is a very reasonable inference that if you have one that has it, one that doesn't, and one's an OEM model, one's a branded model, that at some point someone said to remove this feature. So I think it's a pretty reasonable assumption there. This is a screenshot from the AT&T one. This is my gateway at home, and this is the administrative interface. It lets you configure what subnet you want to use, what range of addresses you want to use, the DHCP release time. It's got another link for IPv6 as well, but it doesn't give you the recursive DNS feature, which is odd. Here's some other screenshots from the same model device. This lets you configure the MTU on the modem. I have no idea why I would do that. The documentation says you can set it as low as 128. So I don't, whatever. This is the advanced firewall page, and it's probably too small to read, but all these options are of the form, mess with my packets, yes or no, default yes. And I've toggled most of them to not mess with my packets. So it doesn't seem to be a reason to, preventing the user from shooting themselves in the foot does not seem to be a reason for removing these configuration knobs. This is a screenshot from, I believe this is the PACE 5268AC, and right in the middle of the screen allows you to manually specify DNS servers. So this is the feature existing in the unbranded OEM firmware image, right there. And I went looking for more external validation, and if you go to OpenDNS's Knowledgebase, they'll have documentation for a large number of home router devices, how to configure the router to use OpenDNS, and they've listed AT&T as well, and they've said, unfortunately, due to restrictions, you can't change the settings on this device, but you can do a workaround where you manually configure everything. This is a semi-official Comcast Support forum where they say the same thing. You can't change the settings on the Comcast-supplied devices. As a workaround, you can manually configure everything. So yeah, there's these workarounds. I don't like the workarounds in particular because only really motivated and technically adept customers will pursue them. They require time and money. For instance, you might buy another router and cascade it behind the ISP-supplied router, but you might be double natting all your traffic. In general, it takes time and money if you want to choose another recursive DNS provider. So the end result is the vast majority of customers, they're completely unaware of DNS and are unaware of the management interface and the fact that they can choose another alternative service. You have a small group of customers that want to change it but can't because they are just prevented by the firmware from doing that, and they don't want to, they don't have the skills or time or money to introduce a workaround. And there's a very tiny group of customers, let's call them network engineers, who can build their own home network and work around that. That middle group is not really, it's not a statically sized group. I mean, if they could make a choice, very simple, by just putting in a new IP address into the management interface, you could market to that, group and grow the size of that group. And, but you don't because you have these firmware restrictions preventing a large number of people from doing that. That's about it. I mean, to conclude, I got a couple of questions here. Is this good or bad, or why is this being done mostly by large ISPs? It seems to be, the large ISPs that have control over their supply chain that can produce custom gateways. The smaller ISPs aren't doing this. They don't appear to be using custom firmware and the devices that they're using to support this feature. Is there perhaps a legitimate reason to do this? Is there a customer support reason or security reason to do this? If so, is there a way to achieve the goals of that customer experience or that security reason while still allowing this choice of a recursive DNS server? I've not seen any official rationale of why this has occurred. I've only seen documentation of this is not supported. So that's my talk. Hopefully people will have some questions or observations or comments.
Hello, Medica KO Farsight Security. I have a comment and a question. One of my comments is I wish that they would actually have capability for not having admin that can't be changed from a security perspective. But my question is more, have you observed whether or not the recursive servers are internal to the Comcast AT&T network? Because I'm wondering whether or not some of them that are locked down are using things like the Quad 9 or 8.8.8.8 or, you know, those public services.
So you can just, so to your second point, you can just take a device and look what options get advertised by DHCP. And for Comcast or AT&T, they advertise the any casted addresses of their resolver clusters. So they're the official resolver clusters operated by the ISP. You know, 75 Quad 75 for Comcast and something else I can't remember for AT&T.
Yeah, the only reason I ask is because about a year ago I had a conversation with somebody and we were discussing ISPs and what they do in Southeast Asia, and a lot of them actually use the public ones. And so I'm wondering whether or not the ISPs are actually maybe locking that down to the public ones rather than using internal.
Ray Bellis, ISC. Thank you, Rob. That was fascinating. Those of you who recall the work I did back, well, 10 years ago now, I suppose, on 5625, and looking at home gateways and DNS. I was sorry to see this is actually getting worse than it was 10 years ago. Can you tell from what you've looked at whether any of these sort of forwarders or proxies are actually doing any DNSSEC on these lookups? It would be particularly puzzling with Comcast being such strong proponents of DNSSEC if they weren't.
So the two providers that I have personal knowledge of, it doesn't look like they're using a DNS proxy or a forwarder running on the device itself. They're advertising, you know, the public address. They're taking the public addresses of their resolvers, you know, 75 Quad 75, and distributing it directly into the.
Okay, well, that's something at least.
So it is a good practice according to your RFC, I believe, to do that. But my point is, you don't get to choose which option gets which IP address gets advertised in the DHCP option.
Yeah, and certainly one of the problems I found back when I did that CPE survey was that on some router vendors, even if you were able to override the settings inside the router, all that would do would change the address that the router would proxy to, and the router would still advertise its own address in the outbound DHCP, which was no better, really. Yeah. Okay, thank you.
Brian Connery, ISC. I can't name names, but I do happen to have some knowledge of some ISPs and what they do and the business cases that they may have. And I think some of it might be motivated by some of the value-added services that they have. Some of the parental content filtering and things like that, I know are implemented at a DNS level. And so I'm speculating here that perhaps some of the motivation for locking down the CPE devices is to reduce customer service problems, because a customer is paying extra for content filtering and they didn't realize that they set their router up to use different DNS servers, and now they're not getting the content filtering, and so they complain, and just...
Right. Yeah, I understand the argument. I have 2 points to make. One is that content filtering is something you opt into or opt out of. In this case, you can't opt out of it. And secondarily, these devices are remotely manageable by the provider. So if you do opt into some of this filtering functionality, the provider can reach in and configure it correctly. So I'm not sure if that explains why this issue has arisen.
Jeff Houston, we do a lot of end-user measurement, a lot. For example, inside AS7922, which Comcast Vote would recognise, 95% of their user base used Comcast DNS resolvers, 5% don't. Now, what we actually find is that across most of the developed world, there's a huge prevalence of the use of the ISP's own resolver, obviously, for reasons like you point out. Behind that, I think, is the whole help desk and reliability issue. Narrow down the number of variables the user has, you eliminate the number of junk calls you get. That saves you a huge amount of money. Google, in particular, which has around 13 to 14% of the world's share of DNS resolution, put most of its effort into promoting the service in the more developed parts, the more developing parts of the world. So Africa, very high. Some countries in Southeast Asia, high, some not. In terms of total population, China is a big user of Google, as is the US in smaller ISPs. And typically what we see is, with a very small number of exceptions, it's the end user that opts to use an open DNS server, not the ISP. The only time I ever saw an entire country go to Google was Vietnam, and they've now stopped it. So I think a lot of this is what you're seeing is simply, I want to package the internet. Having the DNS as something you kind of play around with is not part of a packaged service, because I really want to do this as cheaply as possible. But if you're honestly interested in the breakdown of the resolvers people use, there's certainly some rich data out there that is possible to look at.
Thank you.
Hi, my name is Andrew Sullivan, and I never speak for my employer at the microphone. One thing that occurs to me in looking at what you're saying, and I don't want to speculate why any given ISP might be doing this, but I know that a lot of efforts on finding infections on various systems depend on looking at what people are looking up. And so if you're a large ISP and your costs go up as you've got infections on your ISP network, then it makes a lot of sense to look at that traffic and look for those patterns. And so I can see a reason why, from the point of view of a network operator, it would be really highly advantageous to make sure that people had to use your resolver, because the first thing, of course, that any attacker would do is come in and change the DNS that that the systems are using. Now, of course, this doesn't solve the problem that you can change the DNS on the individually infected systems on the network. But maybe you can do some kind of heuristics with that with very large numbers, the way these particular ISPs do. Maybe the reason smaller ISPs don't do this is because they don't have the staff to be doing those kind of network forensics and so on. So I can see actually a pretty good internal reason for this, but again, I'd be speculating. I know that there are certain enterprises that use that justification for their network practices.
David Lawrence, for all of those cases that were brought up, though, I think I share Robert's perspective that there are other ways of accomplishing those things that do not involve removing your ability to make differences. And in fact, the package internet idea is really interesting because, as you pointed out, there are a number of parameters that you can set that would make no sense at all to even change. And yet there they are still exposed to be able to change them if you wanted to. So unfortunately, I don't have any direct answer myself either, but I see this as a problem that, like, if I wanted to monitor my port 53 traffic on my network, well, I certainly have a lot of other ways of doing that without having to put up my own DNS server and look at its logs. And if I wanted to provide a prepackaged internet, that I could put up a warning saying, hey, if you change your DNS servers, be aware that this could break your filtering services. And yet you would still then have the option to do that. So this taking away the choice does seem to be a very deliberate action on the part of providers that go beyond what seems to be well, we just want to reduce support calls.
Paul Hoffman speaking to exactly what David just came up with. A few years ago, I was setting up a middle box lab, which didn't go very far. Unfortunately, some of you have heard my presentation and haven't heard any follow-up. Things got busy with other things, like the KSK rollover. But when I wanted to be doing that, so I started talking especially to cable providers on this, which is a large percentage of the broadband population. DSL is falling rapidly. Even though you use DSL as an example, I have DSL in my house. We're in the minority. And when you talk to the DOCSIS folks, by the way, if you had a DSL modem, it would have a very similar look to what you had on that, which is you really can't change your DNS, and you can change a million other little weenie parameters. And so I had that question, and the answer is, in fact, that for a lot of those parameters, they can't easily change those from the central location. They want to be able to change a lot of things. But those are ones they can't change because the only reason you would be changing them is in sort of an emergency anyways. So they give you a lot of weeny little things, and they'll say, does this one say yes, does this one say no, okay, switch that, or whatever, in a support call, and they have scripts for that. And they really don't want you changing the DNS exactly for the reason of it just makes their life easier if they know where you're getting your DNS answers from. Now, the funny part of this is there are plenty of, at least in the US, small cable companies, like really small cable companies. I mean, people here might not know, but in the US, there are cable companies with 10,000 subscribers and that's it. They're like part of a town. And what they do is they forward all their recursor, they have the recursor come to them, to an IP address, one of their 5 IP addresses in their own ISP, and they forward everything to 8888. And that's something that Jeff has seen in various ways. But they do that until they feel big enough to run their own. But in fact, in the DOCSIS spec, it says it has a list of parameters that a DOCSIS compatible modem must have, user settable, and that's a lot of those ones that, like, set your TCP, buffer size and stuff like that, which seem really weird, and ones that are optional, and DNS is definitely optional. I don't think that there is an equivalent organization for DSL providers. There probably was 20 years ago, there isn't now. But DOCSIS and EuroDOCSIS and AsiaDOCSIS, they pretty much all agree on these. And they made that optional specifically because, as an organization, they think that DNS is something that is supposed to be done by the head end. Now, again, many of them are doing it by handing it off to Google, or maybe some of them will mistype it as 9999 now. But that is sort of the expectation of the organization for cable, at least. And that will probably change over time. I mean, I looked at this a few years ago. That could be different today. It's a very active organization. They really do care about their internal structures, and they're very cooperative with each other. It turns out that even though you see one cable company, at least in the US, buying another one or buying parts, or people here are probably, who are cable subscribers, are familiar with having your cable company changed on you because someone bought it. They're really good with working with each other on this. And so I would say, if this is a big concern to you, you should actually go to the folks who do DOCSIS and try to push this as something, and not just say allow them in the modem, but actually give them an easy way of changing that if they want, because we are seeing new services that people might want to change to.
Okay.
Quick thought about that, because the fact that it's in the DOCSIS spec as explicitly listed as an optional parameter, that also gives reason to suspect that because it's part of a standard process, that it should have some rationale associated with it, and that would be the place maybe in just going to them and saying, hey, we should really make this a standard settable feature, then maybe the rationale for why people want it to be optional will come out.
Ray Bellis again. To answer one of Paul's comments, I think the guys that mostly the DSL guys use, it would be the broadband forum specifications, which is TR124.
Yeah, are they still active?
Well, not necessarily. I mean, the document itself hasn't been updated since 2006.
Right.
And there's in that particular document, it says that the device should allow the user to specify their own DNS settings, but it's a should, not a must.
Thank you, Robert. Okay, before you all leave for lunch, Keith has some words to say.
Thanks, Ralph. Okay, just a quick one. Yeah, we only planned to have a 90-minute lunch break, but we're running somewhat ahead of schedule. So basically, you get a whole 2 hours. No? 1 3/4. Well, 1 3/4, yeah. So please, if you can be back at 2 p.m. sharp and not wander off too far, that would be helpful. We like to get feedback on the talks that have been given. That feeds into the program committee's process for comparing their ratings against your ratings, so that we keep the material interesting to you. So the first survey is available. The URL will come up on the rolling slides shortly. So if you could start doing the survey, that would be excellent. Don't forget that Jerry is doing demos of the cool new software tools that he's been developing. There's plenty of time to go and see them during the lunch break. Also, the social this evening, you will need your badge for admission, so please remember to take your badge for the social this evening. Okay, so back at 2 p.m. sharp, and talk to you over the lunch break.